Alright, welcome back everyone to this series of videos that are dedicated to text modeling. Today we are going to talk about Word2Vec. So if you're looking at this video, I kind of guess you already know what it's about, or maybe that you Googled it or heard about it. If you don't, I would say from today's perspective, it's still considered to be a rather old model. I think it's more than like 10 years now that it has been developed. Still, to me today, it is an important model to start learning about the concept of like embeddings, word embeddings, document embeddings. And yeah, so I would say let's take a quick look and try to understand its basic functionalities and maybe also quickly talk about what you can do with that. All right, so let's go. As always, here you can see a notebook. I'm trying always to upload it to GitHub, and then yeah, in the description of the video you're going to find the link to this notebook. Actually, this is a notebook that I also use for teaching, so maybe it's a little bit more than for a common YouTube video, but still I hope it helps. So also here, if you would click on those links, you would be sent to the original papers about Word2Vec. But in this video, I just want to give you an intuition how it basically works. So the first thing, which is obviously the most important one, is that now for Word2Vec, what the overall result will be is that we have, starting from what I call here the raw corpus, so that is a collection of documents. Each sentence here is considered to be a document. We're going to end up with a dictionary, so those would be the unique terms in our document. And once we are done training a Word2Vec model, we will have numerical representations for every unique term here. And in that case here, a numerical representation usually is what we call a vector. So if you're not that into math, you may picture also a vector just as a collection of numbers. So, and the amount of numbers being what is called the dimensionality. So for instance, if you would try to create a vector for vanilla, we need to define the dimensionality. Actually, that is also happening when you would train a Word2Vec model. So I would say, okay, I want to create, let's say, 5-dimensional word embeddings. That means for every word or term here, sorry, I was using this in kind of a synonymous way, I'm going to need 5 numbers. And the result of the Word2Vec model is going to be those 5 numbers will be different to the numerical representation of another word if the meaning of the words is similar. And this is kind of a magical thing, especially when you think about this being now in the times where this model has been developed, where I would say more or less many people, especially in research not directly related to language modeling, more or less we're using frequency-based modeling approaches and still just count the number of words in documents to work out what is included in the documents. And here we have something magically happening, such that we have numerical representation of words that kind of capture our understanding of language here. And to get the idea how those word embeddings are created, I think it is good to know or to understand that what stands behind the what we call here the training of the word embeddings is as always for machine learning, some kind of optimization process for a model. And the model is, and that's also the good thing, it's not something where we need to annotate or label something. The model is just using text as it is and tries to, by making predictions of words, to learn and understand the meaning of words. Okay, so that may sound very abstract if you hear about this model for the first time. So let's quickly take a look at some examples. But what we, for instance, have here is, let's say, a sentence like this. So depending on the exact algorithm that we use, it will always be something like, okay, considering that I observed the word I and love, and I observed the word ice and cream, what's the probability of observing the word strawberry? And the first step to do so, So what I'm explaining to you right now is what I called the CBOW, or continuous bag of words approach. It's like one algorithm for the Word2Vec model. Is we always have what is called a window, or windows. Like a window would be kind of depends, to be honest. I'm not exactly sure if that's an exact definition, but to me, what I'm always using is like the window size is basically you always start from some word, which I refer to as the center word, or maybe you use that as the word of interest. And if you set the window size, for instance, to 2, that means you go 2 words to the left, or up to 2 words, and up to 2 words to the right. For instance, if you would use the word ice here in that context, you can always go here 2 words to the left, but then maybe only 1 word to the right. And I mean, those are details. If you still would use that example, if you can't now go up to exactly 2 words or not. I'm not exactly sure also how the like more professional implementations of the model are doing this. And the longer the sentences grows, the less important this gets. But yeah, what you always will have, you have this kind of certain slices of documents. So also here it could be a window size of 1. So that means we would have that overall window here, and we have strawberry in the middle and love to the left and ice to the right. We also would have this window here, so we have love in the middle, strawberry to the right, and I to the left. And this is how you create examples for your training algorithm in the first step. Okay, so you always will get a large corpus, usually with a lot of documents, and out of every document, you still, by using those windows, can create multiple examples to present to the model. But every example will be about trying to predict a missing word or multiple missing words, depending on the algorithm, right? And to predict something, prediction with machine learning-based models, and here in that case, it's kind of a special form of a neural network that we're going to use, or that is going to be used. We need numbers, right? We can't just predict something out of the words. So the first step, and now we directly start with the first algorithm, so the continuous bag of word approach. We always need numerical representation of the words. And in the beginning, you can picture like this. They are just initialized randomly. Okay, so that means, let's maybe go first here. So you can see here we have a dictionary with starting counting from 0 and ending with 13. That means we have 14 different terms here in our dictionary. So in the beginning, if we say, hey, we want to create for every of those terms a numerical representation with a dimension of 3, we now have for every word or term here, a 3 numbers, right? Because that's the dimension. And in the beginning, those numbers, they are initially like they're randomly initialized. Okay, so they don't really get the understanding of meaning and language, how we use it at that moment, but that's the starting point. Technically, for instance, to collect them, so let's say we have here, let's say we denote it like this, so x0 and x2 would be the vectors themselves. So if we start with the first example, we have I and love vanilla, and say we have a window size of 1. So that means the actual word of interest is love, and we try to predict love by presenting the model the numerical representations of I and vanilla. So that is to grab those vectors. Usually you start with a 1 hot encoding. That means, as you can see, if we refer to the first word, then we have a vector that has the same length as all available terms in the dictionary, but it's only equal to 1 at that position where the term in the dictionary is, and also then this is grabbing the vector at that position. Okay, so that means if in our dictionary I has the ID 0, its 1 hot representation is a vector that has a 1 at the first position here, so position 0 in Python counting. And that is why, if we multiply this vector with that matrix here, we end up with the first vector here, and that is going to be used as the numerical representation for the word I. And then, for instance, if we want to have like vanilla, right, because we try to predict love, then we start with that 1 hot encoded vector because it has ID 2, so that means it is at third position when counting in Pythonic ways. And if you multiply this vector with this matrix here, we grab that vector here. Okay, so that's how, like in the beginning, as I said, those are random numbers. But still, now we try to collect the vectors for what we can also, maybe if we use machine learning wording here, then those would be the feature vectors, right? Because the features is what we usually use to make a prediction. And if you take a look at the first example here, if you have I and vanilla, those would be like, we give this information to the model. Those are the features. And with the features, we try to predict love. And in this case here, the features are then those two vectors. So with this operation here, building the one hot encoded vectors, multiplying this with is what is going to be used as the feature numerical representations of the words. We're going to collect this and this vector, which are supposed to be the vectors for I and vanilla. Okay, so you can compare it, and this is what we end up. So this is our feature vector. And then with the continuous bag of word approach, what is done is we aggregate the information of those two words. This can be done by summing them up, the vectors, or by averaging them. And in my example here, I'm just averaging them. That means if you average a vector, it's just as you would do it, from element to element with just a usual number. So that means you add this value to this value, and then you build like the average value of them. You always also build the average of those two values, and you build the average of those two values. So here you finally end up with a vector that is representing the information that we have I and vanilla. And then technically, now it gets technically here, what we also then have here is going to be another matrix with vectors, and here let's call them the target vectors. It has the exact same dimension. Also, at the first position, it's going to referring to the word I. At the second, it's going to referring to the word love, and then here to vanilla, right? So that is what is then V here. But yeah, so we have one set of vectors that are going to be used when we use them as the features. And we have one set of vectors that we are going to use them if they're going to be the target. And the target here is love. And so if we then take a look here, right? So maybe let me just show you this, because so that is how V is going to, okay, sorry, here it is internally. It's be the weights. So that is how those vectors look like. So if you want to compare them, for instance, just the first position, that is how the vector that is going to be used if I is used as a feature is looking like. And that is how it's going to be used if I is used as the target here. And with this information here, like the feature information, we now try to make predictions, probability predictions. So in the first step, what you do, if you're used to multi-class classification with neural networks, then you can kind of, then you kind of know already. But if you don't, what you do here when you execute this here is you're creating what I refer to as scores. Okay, so we quickly take a look. Here they are like somewhere between -1 and 1, I would say. But you basically do is you multiply this vector here with every vector in the matrix that includes the embeddings for the target words. So what you intuitively doing here is you multiply the information with all potential targets, and all potential targets are all all terms in dictionary. And what your overall goal will be is that at this point, for instance, if we have I, love, vanilla, information is I and vanilla, then at some point, once the model is trained or better trained, so that means the vectors for the features and the targets kind of understand a little bit about the meaning of the words. You want to have, for instance, a relatively high score for vanilla. But at the same time, you also, for instance, if we take a look at this example sandwiches here, like if you present I and vanilla and I and strawberry, in both cases, for instance, you want to have relatively high values for love, because the score is later going to be transformed by what is called the softmax function. So basically transforming those values here, which can be any real numbers, into numbers between 0 and 1. And then they are interpreted as probabilities. So if you have a high positive score, after the transformation, it's going to be a high probability. And your overall goal will be that if you present I and vanilla or I and strawberry, in both cases in our example corpus here, the center word is love. So if your model observes this as information and it has been trained successfully for a while, you want to have a high score or a high probability that the actual word is love. Because finally, this model is trained as a multi-class classification problem, or you can picture it like this. Technically, it's done in a slightly different way due to some issues here, but that they are more relevant for really realistic and large corpora with a lot of number of unique terms. But finally, what will be here, you have and this is what the intuition here is about. You have created a numerical representation of the information. So here the information is that we have I and vanilla, or I strawberry in the next sentence. And then you try to make probability predictions. So here we have again 14 different unique terms, and every number here is the probability that this word is in the middle, given the information that I and vanilla or I strawberry are the feature words. And as I said here, in the beginning, if this is randomly initialized, then they are really similar to each other. But at some point later, when the model is trained, and this is the probability for love, in a well-trained model, the probability is supposed to be very high, because that is what we actually observe. And to train the model, this is like a multi-class classification problem. You use a loss function. Here it's the negative log of the probability prediction for the word that we actually observe. So if the actual word is love, then we would calculate minus log of that probability here. And here a loss function is always defined in a way such the lower the better. And all the parameters of the model, so that means the vectors here from the features, also the vectors here from the target words, they can be changed, or they're going to be changed by that information that is presented here. But yeah, I think in this model, let's not stick too much to that, because that's more like a general issue, how you train a neural network, how you train any or the most of the machine learning models. But the intuition here is you're going to present the model a lot of those examples. And whenever you see such an example, you can evaluate the prediction by this loss function. So that means if that value in that moment here, like the probability for the correct word, is really high, then this value is going to be low, and the signal to like the parameters of your model will be, like loosely speaking, okay, you're quite okay. We may slightly adjust you a little bit to even be a little bit more, to create a higher probability when we see this example for the next time. But if the probability prediction here is rather low, then the model is more drastically changing the parameters in a direction such that the next time we would present this example and recalculate everything, that the probability is going to be higher the next time, right? And if this is done with different examples for multiple times and many iteration steps, the model is slightly improving more and more, and also obviously more in a general way, especially if you use a large corpus with many different text examples and different windows and window sizes and so on. All right, so before we take a look, go further here, this first video about Word2Vec is really just to get the intuition and understanding what it is about. And if you bring it down, I would say it is about that you start with a large corpus, you extract the unique terms here, and then you give every term here two vectors. One vector is referred to as the feature vector, and the other vector for every word is the target vector. And then out of the original text, you are going to create many different examples by setting a window size. And if you use the continuous bag of word approach, then you always try to predict what I call a center word by presenting the words surrounding the center word. The number of words you use is defined by the window size. And yeah, then the model is going to be trained. That means the model is going to present many different examples, and always the parameters of the feature vectors and the target vectors are changed in a way such that the probability predictions for that actual word that we observe is going to be as high as possible. But here in a more general sense for overall all the examples that we create out of the corpus here. All right, so this is how the continuous bag of word approach works. I mean, if you go by yourself, if you would go through the notebook I'm adding here, you can see I kind of implement here are shown the examples and kind of train the model by myself in a simplistic way here. So, but for instance, here, even with our example, if you would now take a look at the vectors, and we're going to talk more about this in the next videos, what you can do is you can use a similarity measure that is used for vectors. So, Euclidean distance could be a choice, but it's more common to use the cosine similarity. But basically what that does, it is a metric that is technically between -1 and 1. And if you input two vectors, it will output one scalar value. And the more close it is to 1, the more similar the vectors are. And in our example here, I would say one of the reasonable examples would be, or what you can observe here is that if you take a look at the similarity between strawberry and vanilla, it's really large. It's almost close to 1, which is reasonable because we see in our original corpus, the model tends to understand that here vanilla and strawberry are both tastes or something that has related to ice cream and love, and so which is good in that context here. But it understands, even though the words are different, that their meaning is similar in terms of it kind of describes something that is related to ice cream. Okay, and this is, to me, still quite not magical, but I think this is very impressive that a model is able to learn the meaning of words. And in the next video, we quickly take a look at how the model is learning the similarity. Quickly also take a look at the other algorithm, but I think it's not that important to really be that well educated about all the specifics of the algorithms, but because especially in reality there's much more to do. So this video is just about the intuition, and then in the next video we also want to take a look where the similarity actually comes from, kind of as a repetition to what we've been discussing in this video. And also, and even more importantly, if you would like to use those models, how you can use them, what you can do with them, and and that's mainly it. And especially then, if you're really interested in training your own word models, I think I'm also going to do a little video on how you do this with a very powerful and well-written package here, which is the GenSim package. All right, but this is going to be content of the next videos. So see you there and take care. Bye-bye.